And for time domain analysis, we go for state space because in state space analysis, we treat time as the independent variable. So that's just the feeling that you have already got. So today, I think we'll be doing a couple of circuit examples. I believe you have not been formally introduced to the topic. You have not been formally introduced to the definitions of state. What is a state? What is a state trajectory? What's a state space? So we will not go into that. We'll just take some circuit examples today, and so that you get a feeling of how to, do analysis of proper circuit analysis. So what we'll do is we'll take some example from the book. Okay, and I recommend you just have some notes, take the notes, and we'll just do it together. Okay, before we take some example, I will just write the equation that you may have already seen. Is the board clearly visible to you?
Yes, sir.
Okay, good. So for state space, the general equation looks like this. Isn't it? So what I've written on the board is a general representation of a state space model. You may have already seen the equation, but today I will just tell you some of the information about this equation. So this one is known as the state equation. And this one is the output equation. Okay. So what does this equation basically tell you? The first equation tells you that this x that I marked over here, let me change this x is basically what you call the state vector. Okay, now let me just mark it here. X. This is the state. This is basically a vector. It contains entries which are known as state variables. And what I've written is here is x lives in a dimension n, where n are the number of state variables. That's the number of entries of x. Okay, simple. So x is a vector and its entries are n, and each entry corresponds to a state, and this x is the state vector, this x. Next is this u. This u is nothing but the input. Let's suppose, first of all, we can have two kinds of models, as you know. One is a single input, single output. Another is a multiple input, multiple output. We'll discuss both of them, but here I have assumed the system to be single input, single output. So this is just a one entry. This is just a single input, u. Otherwise, if it had been a multiple input, then it will have been multiple entries. So here I have assumed u to be a single entry. Similarly, y is the output, u is the input, and y I have assumed to be the output. Okay. So for single input, single output, this is just a single entry, and this is also just a single entry. This is also your input. So just focus on the first equation. What does the first equation tell you? The first equation tells you that the flow, or we can say the rate of change of the state variables, that's a linear combination of states and a linear combination of inputs. Because this A and B, they are just matrices, isn't it? Your A and B are simply matrices, or it can be vectors in case of single input, single output systems. So this becomes a linear combination of states and a linear combination of inputs, and that's given by this equation. What does the second equation tell you? Second equation tells you that the output, this is the output vector or measurement vector. That's the variables that you're interested in capturing about the system. This output equation, it's also a linear combination of states and some term corresponding to the input source. Okay, that's the information that's being given. There is no nonlinear terms involved here because this is just a linear combination of two entries. And mind you, this first equation is a set of, like I may have already told you, this is a set of n first order equations. Why I'm saying it's a set? Because I'm assuming that there are n equations. And since you're seeing only a single dot, so that's a first order system. So I'm having n set of first order equations. Sorry, first order differential equations, because this contains the derivative part. And the second equation is an algebraic equation because there's no derivative involved. So the first equation is the set of n first order ordinary differential equations, and the second equation is a set. It's also a set of n algebraic equations. Okay. So coming to the dimensions, if we just see what the dimensions look like, and I will just rename these matrices as vectors as matrices now. This is a matrix B, and this is a matrix C. We'll just keep things very simple. So if we have assumed n state variables, if we assume n state variables of the system, then can you tell me the dimension of xt? What will be the dimension of xt then? This. What will be the dimension of xt if I assumed n state variables? Anyone? What will be the dimension?
So, excuse me.
Yeah.
So, can you just explain the n state variables part? I didn't
Okay,
understand.
sure. What I've assumed here is first, like this I told you, this first equation, this is a set of n first order ordinary differential equations. Basically, this is a matrix A, and this is a matrix B. Okay, I will just make a diagram here so that you may better understand it. Because this state space is usually represented in a matrix form. This looks like this. This is your x dot. This is your A. This is your x. This is your B. And this is your input term. This is how a matrix form of the first equation looks like. So I'm having n entries for this matrix. This is having n rows. Similarly, this A matrix, this dimension will be n cross n, isn't it? What about its x? We already assumed it to be n cross 1. What will be the dimension of B? If I have assumed a single input, single output system, this is just 1 cross 1 entry. So what would be the dimension of
n cross 1?
N cross 1, exactly. This will be n cross 1 because this has to satisfy n cross 1.
Yes.
This is how state space set of n equations looks like. Okay, but mind you, I have assumed a single input here, isn't it? I have assumed
Yes.
a scalar. Had it been a multiple input system, had
Like
it been
another matrix
let we assume that the inputs are u. One second. If u are p, I mean I'm having p inputs. This is the advantage of state space. In a transfer function modeling, we cannot do simple analysis for multiple inputs and multiple outputs. If I assume p inputs and q outputs, we can have inputs coming from different sensors, for example, and if you're having outputs, you are having some measurements, and you're measuring q entries for a system. So what will be the case in that? It's a p cross 1 matrix, isn't it? This is not a 1 cross 1 entry. 1 cross 1 entry is just one single input, single output system. For multiple inputs, having multiple sensors, you are having, let's say, p sensors. So this will be a p cross 1 vector. And this b won't be a vector then. This will be a matrix. And matrix is represented by capital letters. So this will be a matrix. It will be just like this. This will be a matrix. And you will be having a vector of views or vector of inputs. This is p cross 1, and this dimension will be n cross p, isn't it?
N cross p, yes.
You can see the A matrix hasn't changed because this A matrix doesn't capture this information about the inputs. This A matrix basically tells you what's the relation between the states and its derivatives. This matrix is just for that. This B matrix tells the information how the inputs come to the states, how the inputs are entering the dynamics. This is told you by the B matrix. And if you have single input, then this is just a vector. And if it's a vector, if it's a multiple inputs, then this will be a matrix. And these are the general dimensions. Has everyone understood it properly?
Yes, got it.
Okay. Now, what is the second equation? The output equation. The output equation looks like this. Y is equal to Cx plus du, isn't it? And in matrix form, it looks like this. Okay, I have assumed here multiple. I have multiple outputs also, isn't it? I have q outputs. So what will be the dimension of first of all the y? It's q cross 1, isn't it?
Q cross 1, yes.
So this is the vector. This is your y. Q cross 1. And this is equal to this is Cx. I'm just writing here Cx plus some d. I will not mention the dimension first. I will just write you the. You will tell me the dimensions plus du. We have fixed the dimensions of inputs and outputs. Input I'm having q majors, and for inputs, sorry, outputs I'm having q, and for inputs I have assumed p, isn't it? I'm having p inputs and q outputs. And the dimension of x is already fixed, n cross 1. We have n states, isn't it? What is the dimension of c?
Q cross N.
Okay,
Q cross N.
q cross 1. What is the dimension of d then?
So Q cross N, right?
Sure.
Q cross P.
Yeah, it will be q cross p. Just check the dimensions if they match. This is q cross 1 into n cross 1. This will give you, no, this is not q cross 1. This is q
It
cross
is
n.
Q cross N, right?
Yeah, this will give you q cross 1. And what about this? This will give you q cross 1. And that can be added to give you q cross 1. So that's why it's a matrix. See, if you have multiple outputs, then this will be a matrix. Otherwise, this would be a vector, just like B matrix. Just like I showed you as a B matrix. So as your inputs are increasing, the columns of B will increase. As your inputs are increasing, otherwise it's a vector. Similarly, the argument for C. As your outputs are increasing, the rows of C will increase. Otherwise, it's just a single row. Okay. And for single input, single outputs, your Q equals your P equals 1. This is a special case which we call single input, single output. P and Q are just 1. Your B is a vector, so is your C is a vector. And for multiple inputs, multiple outputs, your B becomes a matrix and your C also becomes a matrix. That's the only difference in multiple input and multiple outputs. Okay? Has everyone understood this equation, state equation, and this output equation? Any confusion in this?
No, sir.
Okay. This will be properly introduced to. Don't worry about it. If you don't understand it right now, we'll properly introduce to the states, the state vector, the state. You just have to do multiple revisions. So don't worry about. We will just take some examples to get you some feeling of how to do it. We'll take some circuit example. Just write it down. This example 1. You will just get the feeling of how do we insert the entries in these matrices. This is your R1, This is your L1. This is your L2. This is your R2. And this is your C. And this is your I1 current, and this is this branch current is I2. Okay. And here it's assumed that the output is measured across the I2 is your output. So what you have to do basically is to obtain the state space model of this LTI system. First of all, before you start doing the state space analysis, what you have to do is to identify the inputs and the outputs. So here the input is this excitation source, which is ET, can be voltage source, which you have represented because in state space modeling we represent inputs with U and outputs with Y. That's like I showed you. So this is your input, this excitation source, and the output is taken this current, this branch current, this I2. Okay, so you have to keep that in mind. What's the input and what's the output, and you have to derive a state space model for this system. Before we start, can anyone tell me what will be the dimension of the state space model for this kind of circuit? Yes. What will be the dimension? You can just take a guess. What will be the N that I showed you in the general representation? Okay, how many energy storage devices are in the circuit?
2 cross 1.
3.
Sorry?
3 है sir 3.
Q. No, I'm just first of all tell me how many energy storage elements are there.
3.
sir.
3.
You understand energy storage elements?
Yes.
There are 3 energy storage elements. So we have 2 inductors and a capacitor, isn't it? These resistors are not considered energy storage elements. For circuits, when we do the state space models, we have to identify the energy storage elements. That will give you the information of the state variables. So you have 3 energy storage elements. So the dimension of the state space model will be 3. So what you have to do is first label the states. Okay. So this, what is the physical variable associated with the inductor? That's the current. Current. Yeah, that's the current through the inductor. And what about the capacitor? That's the voltage across the capacitor.
Voltage.
Isn't it? That's the dynamic variable that we have selected. For inductor, the dynamic variable is the current through it, and for the capacitor, the dynamic variable is the voltage through the capacitor. So your first state variable will be the current through L1. I will rename it as X1. You know we mentioned the state variables as X1, X2, and so on. So your first state variable is the current through the first inductor. Okay. The second state variable that you will select will be the current through the second inductor. And the third state variable will be the voltage across the capacitor, which is the only capacitor. You can mention it here, X3, which is also your voltage through capacitor V. That's V3, or V. You can mention V. This potential between the capacitor. That's your state variables. And you don't have to worry the order of this. You can mention any one X1, any one X2, any one X3 because the state space presentation is not unique. So you don't have to worry which among the 3 I mentioned X1 and X2. You can have it in any order. But you have to just keep in mind that you are labeling the correct dynamic variable. You have to label the current through inductor as one of your state variables and the voltage across the capacitor as one of your state variables. And since in this circuit you are having 3 energy storage devices, so that will give you the idea that you will be having 3 state variables. Is it okay?
Yes sir.
Okay. Once you have labeled your state variables, this current I1, this current I2, and this voltage V3, the next step is to write the equations. Okay, we'll write the equations, the KCL equations for the circuit. And you have to also keep in mind that I2, that's the output. Okay. what you can do is you can apply KVL in this loop. Just apply KVL in this loop. The first loop. We have this ET, or you can say simply UT. This is equal to what? The sum of, if you move along this loop, that's voltage drop across the resistor, which is what? I1 times R1, isn't it? And since, okay, let me first write it. R1 times I1 plus L1 di1 by dt plus V. Is it correct?
Yes, sir.
I'm just applying the KVL in this first loop. This voltage drop will be the sum of this, and this. This is R1 I1. This is LdI by dt for the inductor, and this potential is V that I already mentioned it here. So now I don't want these parameters I1, I2 because I labeled I1 as X1 and V as X3. So instead of I1, I will use X1. Instead of V, I will use X3. So what will be the equation look like? UT equal to R1. Instead of I1, I will write X1 plus L1 instead of di1 by dt. That's what? X1 dot derivative of X1, because X1 is I1 and derivative of I1 is X1 dot, isn't it? Plus, instead of V, I will write X3. Is it okay? And solve this equation for X1 dot. X1 dot will be what? Minus R1 upon L1 X1 minus 1 upon L1 X3 plus 1 upon L1 U. Isn't it? Is it right?
Yes, sir.
Is it okay? Simple mathematics we are doing, no fancy thing. We just applied the KVL, and instead of this I1 and V, instead of currents and the voltage, I have just labeled as the state variables, and I got my first equation for X1 dot. Okay, now do the same for this loop. This voltage will be the sum of these two voltages, isn't it? So here, this voltage is X3. So X3 is equal to what? What's this voltage? What's
LdI by dt.
in terms of X2?
LdX2 by dt.
L2, can I write it
X2
X2
dot.
dot? Is this voltage L2 X2 dot, L2 and di2. di2 is X2 and X2 dot plus this voltage. What's the voltage of across this resistor in terms of X2?
R2.
X2R.
Yes, R2 X2. So this is the KVL across this branch, and solve this equation for X2. X2 dot. This will be what? Minus R2 by L2 X2 plus 1 by L2 X3. Is it okay?
Yes.
Okay. This is your second derivative of X2. So far what you have obtained is the first X1, the derivative of X1, and now we have got derivative X2. What we need is the derivative X3. So this is just circuit example. We are just doing some analysis about the circuit. What will we have applied so far? KVL in this branch, KVL in this branch. Okay. How can we get the derivative of X3? Any idea?
By applying equation on capacitor.
I1 minus I2, sir.
Yes.
Equation became
There are a
capacitor.
couple of ways you can do it. In circuit analysis, there are a couple of ways you can do it. What is this current through this capacitor?
I1 minus I2.
I1 minus
Yes, that's I1 minus I2. Or simply you can say this incoming current, this I1 that's being injected, this current is the sum of that's going through this branch and going down, isn't it? What I can write here is I1, this I1, that's the sum of this I2 and this current that's going down through the capacitor. That is equal to C dV by dt. Is it correct?
Yes, sir.
I1 is the sum of I2 and this current. Now rewriting it in terms of state variables. Your I1 is what? I1 is x1. So x1 is equal to what's I2? I2 is x2 plus C. What's V? V we have labeled as x3. So that's x3 dot. Is it okay? And we can solve for x3 dot. What's x3 dot? It's 1 by Cx1 minus 1 by Cx2. This is your equation for x3 dot. Is it okay? Everyone understood these three equations?
Yes, sir.
Now we can write it in matrix form, just like I showed you. In matrix form, you will be having like this: x1, x2, x3, and these are the dots. That is equal to. You'll be having a matrix A, x1, x2, x3, plus you'll be having B matrix into U. And now you just have to fill this A matrix and this B matrix. So what's the equation for x1 dot? See, the x1 dot has some relation with x1, x2, x3 and U, isn't it? So that's what we'll be getting here and here. That's the relation of x1 dot with these three and this U. Similarly, the term corresponding to x2 dot will come here and so on. So what's the term for x1, or what's the equation for x1? Where have I written that?
Minus R1 by L1.
Yes, this is the relation with x1. This is the relation with x3, and this is the relation with U. There is no relation with x2. Okay, so just instead for the term of x1, just write minus R1 by L1. So here I will write minus R1 by L1, and there's no relation with x2. There's no relation with x2, and for x3, what we have? Minus 1 by L1. Just check it. Okay, coming to x2 dot. For x2, okay, we have also a relation with U. For U, I'll be having 1 by L1, isn't it? That completes my first equation. R1 by L1 times x1 plus 0 times x2 minus 1 by L1 times x3 plus 1 by L1 times U. That's the first equation. Okay, the second equation for x2 dot. I guess it's 0
0 minus
R2
R2 by L2 minus 1 by L2.
1 by L2.
1 by L2.
What's the relation with U for x2 dot? That's no relation.
0.
Okay. Similarly for x3, x3 is here. The relation with x1 is 1 by
1
C.
by C.
The relation with x2 is minus 1 by C. There is no relation with x3 and there is no relation with U. So that's your first equation. You are having three state variables and you are representing the derivatives in terms of the state variable itself and the inputs. You're also having one more equation, y, isn't it? So what I assumed the output in this equation? I assumed the output to be I2. This I2 is the output. And I2 is nothing but x2. So your x2 is the output. Let me just move it here. Okay. So instead of x, I'm first of all write x1, x2, x3, and your output is nothing but x2. 0 times x1, 1 times x2, and 0 times x3. So your y is just x2, and you're having plus du term, isn't it? There is no relation of output to input, so your d becomes 0. So this term vanishes. For most of the systems that you encounter, we don't have this d matrix. However, in some situations in which there is direct relation between output and input, then we have this d term also. Otherwise, mostly for circuit analysis extra, you don't have this term. Okay. So this is your output equation, y is x2, and this is your state equation. That's how you fill the entries. And since there are 3 energy storage entries for the circuit, that's why the dimension of A was 3 cross 3, and this is 3 cross 1. And it's a single input, single output. That's why U is a single entry, and Y is also a single entry. And your output in this circuit is just x2. Your output is itself a state variable. But that's not always true. Output can be combinations, like I said, linear combinations of your state. So that was the first circuit example. Was this? Have you understood everything about the circuit? How we derive the states?
Excuse me, sir.
Is it
Sir,
okay? Yeah.
सर जो आपने आउटपुट इक्वेशन लिखा है वो प्लीज आप बता सकते हैं कैसे लिखा है फिर से?
Okay. See, your output was assumed to be I2. जो सर्किट में आपके पास सर्किट में लिखा था पहले,
यस सर वो मैं
आपके पास इंडक्टर था, this was your output, and I have assumed my output to be x2, isn't it? This is your second state variable. So what will be the equation for y? The equation of y is equal to cx. This is here. Y is equal to cx plus du. Your x is just a 3 cross 1 vector. So what you have to do, basically you have to arrange entries for each entry of C matrix, C vector. So that's 0 times x1 plus 1 times x2 plus 0 times x3. This is basically known as inner product. In linear algebra, we call this inner product. When you have a row multiplying with a column, you will get a single entry out of it. So when you do the multiplication, you will get y equal to x2, which is the equation for output. And you have no term corresponding to d. Your d is 0. So you get the term y is equal to x2. And your output is assumed to be x2. So, okay?
सर
Yeah.
तो इसमें जो हम I1 और I2 दोनों
Sorry.
सर इसमें जो हमें I1 और I2 दोनों के लिए निकालने आउटपुट
अगर क्या I1 and I2?
जैसे I2 आउटपुट है तो वैसे I1 और I2 दोनों क्या?
Sure. Like I told you, it's up to the design process. When you design circuits or when you do the analysis, it's up to you what you take as the output and the input. Here it's assumed that I2 is the output. You can assume I1 also as the output. You can assume the voltage across R2 as the output. It's up to you. Accordingly, the B or C matrix will change. It's basically when you are doing analysis of some circuit, you are just using some measurements. You're taking some measurements. If I'm taking this measurement, the current through inductor, I'm interested in this measurement, so this is my desired output or my measurement value. If I'm taking measurement across this, then this is my output. And what will change if I change the output? Just the entries of matrix C will change. Your A matrix won't change. What's the A matrix? Your A matrix won't change because this depends on the dynamics of the system. This forms the values of R1, L1, C. And if you change your measurement or your desired output, then the entries in C will only change. Had it been output I1, which is your X1, then your C would have been 1, 0, 0. Is it okay?
So this is only for single input, single output.
Yeah, this example is just for single input, single output. We are just having one input, U,
Okay.
and one output, Y. This is just a single input, single output. And how can you identify if a system is single input, single output just by looking from the state space model? You can see from the matrix B and C. like I just said before, if your B is just a vector, single vector, then it's a single input. And if your C is just a single row vector, then you have a single output. Had it been a matrix, had B a matrix and C been a matrix, then from the columns of B, you can calculate how many inputs I have. And from the rows of C, you can calculate how many outputs you have. For this circuit, we have only one input, U, and only one output, I2. That's why this
Excuse
is
me, sir.
Yeah.
Sir, if C is a single row matrix and
Yeah.
all the elements of it is a 1 1 1, then it will be a single output.
Yeah.
Single output.
Calculate if it's 1 1 1, what will be the Y then? Your Y will be x1 plus x2 plus x3, isn't it? If it's 1 1 1, just do the multiplication. X1 plus x2 plus x3. Then you are interested in measuring the sum of all the states.
Yes,
It's
sir.
basically what you are desired, what are you measuring from the system. If someone is interested in the sum of two or any linear combination, not necessary one.
Means the output is a linear combination. It will be
it's a
single
linear
output.
combination of x1. It's basically like this. A1 x1.
It will still be single output, sir.
Yeah, the output is again single plus A3 x3. Had it been like this, then it's a general presentation. Then the entries of your C is A1, A2, A3. It's a linear combination of your states. But still, it's a single output. You're doing
Yes,
the
sir,
sum.
got it.
You're doing the sum here. You will get one entry.
Yes, sir.
You
Got
will
it,
get-
sir.
For example, your states. Let's say your states are temperatures from 3 sensors. Okay, this x1 represents. I'm just giving an example. It's a temperature from sensor, let's say T1, and this is another sensor x2, which is measuring T2. So you will get sum of the temperatures. So you will get finally a single output temperature from all the 3 sensors at different locations. This is a
अगर
single output. Okay.
अगर तो सी मैट्रिक्स कॉलम मैट्रिक्स है तो फिर इसमें हमें मल्टीप्लिकेशन
कौन सा कह रहे हो आप?
तो सी मैट्रिक्स
सी मैट्रिक्स
जो कॉलम कॉलम
अगर ये वेक्टर नहीं होता, अगर ये मैट्रिक्स होता, वही कह रहे हो ना?
नो सर, तो मैं कह रहा हूँ सर इसका जो सर 1 + 3 सर तो
You are saying
सी का डायमेंशन 1
cross 3.
सी का डायमेंशन 1 + 3 होगा.
हाँ, 3 cross 1. Number output comes 1 cross 1. यही कह रहे हो? This is 1 cross 3. This is 3 cross 1. You will get a 1 cross 1 entry as an output.
और 3 + 1 हुआ सर
आपका जो C है, this is basically a row, and your X is a column. When you do the multiplication, you will get a single entry. This is the inner product. You do the entry. This is A1 x1 plus A2 x2 plus A3 x3, which I have written it here, and you will get a single entry out of it. ये पूछ रहे हो आप?
Excuse me, sir.
हाँ.
Yeah. So can you show a matrix which gives us multiple outputs, like a single input, multiple output system? Can you
Yeah,
show the output
definitely.
equation?
We have to take. We will take. Yeah. Yes, we will take some
So
examples.
just can you show it now,
Yeah.
because like I want to differentiate. Like अभी देख लिया हमने
हाँ,
ऐसा
for an
single
example,
system.
see, we will take MIMO systems also. That's the part of the curriculum. We have to take some MIMO examples. I'm just trying to give you a feeling of how the system matrix will look like. We will take an example. If you had been a matrix, I will just give you an
Yes, sir.
idea.
Just the output equation. Yes, sir.
That's the output equation. For general representation, I wrote it here. If you are having P, this is as if you take a general example. This is n cross 1. This is P cross 1. No, we assume Q outputs. Q cross 1. And this will be Q cross n. This will be a matrix. This is still a vector. And this is what? This is Q cross 1. Just like this. We will take an example. For sure, we will take I'm just showing you a general presentation how
Yes.
C will look like.
Yeah,
Because
got
we'll
it.
be having this is the multiple output case. We will take later an example in which you will see the values for it. But before that, we will take another example. Example 2. Don't you worry, we will take some multiple inputs also. Decide another circuit first. This is IP. Once you get enough practice of the circuits, then you can straight away write the state matrix. You don't have to do any, write any equations. Once you get enough practice on this. But right now we are just doing it step by step manner. This is also another example from book. This is your L3. This is your L2. This is your L1. This will be your C1 and this will be your C2. There's no resistor involved. This is your input. A single input. Again. And the output is, output is measured across V1. This is your V1 voltage. This is your V2 voltage. Okay. And this is your output. This is your output. Your output is basically the voltage across the capacitor. That's your interested output that you're interested in. And this is your input. First of all, just identify input and output. This is a single input source, single output measurement, and you have to obtain the state space model. What will be the dimension? How many energy storage elements are there?
4.
5.
Sure.
5.
5.
There are
5.
1, 2, 3 inductors and 2 capacitors. No resistor involved. So there are 5 energy storage elements. So what you can straight away tell is there will be 5 dimension. The dimension of A will be 5 cross 5 and so on. And you just have to label the state variables. Just label the state variables. And you can do that in any order. If first this voltage capacitor across C1, I will make it as X1. X1. Or better to write it here. X1. X1 is the voltage across C1. Similarly, I will take X2. X2 is the voltage across C2. Okay, I have to take the voltage for capacitors. Okay, X3 I will measure this. Current through L1. X4 is this. Current through L2. And X5 is this. Current through L3. So I will label my state variables. These are voltage and these 3 are the currents. So you're having 5 state variables for this. So let's do this example together. Just write, first of all, just write the final structure of what the equations will look like. This will be X1, X2, X3, X4, and X5. And these are the dots. This is your derivatives of the states. We'll be having a 5 cross 5 A matrix, which will relate to these state variables. X1, X2, X3, X4, and X5. Then you'll be having a vector because this is a single input, and U. So you just have to fill the entries for A, you just have to fill the entries for B. And how will you do that? You will just have to use circuit analysis. Just write the equations. Try to do it yourself. And you have to just keep in mind some things. If this is your A matrix, it's not necessary every entry will be non-zero. There are some entries which will be zero, like x1 dot. It will be having just relation with only some entries, so the rest will be zeros, and it may or may not be having any relation with input. So it's not every entry will be all non-zero entries. Some entries can be zero. So first of all, just write the equations. Right? You just have to obtain the equations for x1 dot, x2 dot, and so on. Try to see which one you can get. Because this is all about practice. The practice you have, if you are having enough strong practice, you don't need to write the equations. You can straight away add the entries for here. But right now, do it in a stepwise manner. Write equations for dots related to x1s and u's. There shouldn't be any variable like I3 or V3. You should be having variables like x1, x2, and u. And then we will see what the output equation will look in this case. Just first of all, write KVL in here. That will give you one of the state variables. You just first try and I will show you. This is C1. This is very simple example. There's no resistor involved. Are you doing it? We'll give you just a couple of minutes and then we'll do it together. First, give it a try. Give it a try. Okay, we'll just do it together. See, we'll just quickly write the equations. Okay, let me just show it here. Okay, this voltage, which is your output, actually, this I have labeled this voltage as x1, and this voltage is same across the L1, isn't it? So x1, this is L di by dt. L is L1, and derivative of the current. Current is x3, so that's x3 dot. So immediately you can say x3 is 1 upon L1 x1. That's it. That's the first equation. And the x3 dot, sorry, x3 dot. x3 dot is 1 by L1 x1. This is x3. x3 is 1 by L1 x1, and rest entries will be 0, 2, 3, 4, 5, and this is also 0. That's the equation for x3 dot, isn't it? That's the first information that you obtained. Similarly, you can do this analysis here. This voltage and this voltage will be same, it's in parallel. So what's this voltage? This voltage is x2. X2 is what? L di by dt. L3, derivative of this current, and this current is x5. Are you following it?
Yes, sir.
Okay. This is this voltage I labeled as x2. This is L3, derivative of x5. X5 dot. X2 is L3 x5 dot. So immediately you can have the equation for x5 dot. 1 by L3 x2. Just fill the entries. X3 has only the relation with x2. Sorry, x5. X5 has only relation with x2. So x5 equation is here. It just has the relation with x2. Other entries will be 0. Similarly, no relation with input. Are you just following what I'm doing here in the matrix form?
Yes, sir.
Okay. Move on. Do one thing. Apply KVL here in this loop. Apply KVL. What's this voltage? This voltage is x2. That's equal to the sum of this voltage and this voltage. What's this voltage? You have to tell me in terms of state variables. This voltage is V2 and this voltage is L di by dt. L is L2 and current is x4. So x4 dot plus this voltage. This voltage is x1. So you can get the equation for x4 dot. You just have to separate out the dot terms. Here x3 dot, here x5 dot, and I'm going for x4 dot. That's 1 by L2 x2 minus 1 by L2 x1. That's your another equation for x4 dot. So it has a relation of minus 1 by L2 with x1. x4 dot minus 1 upon L2 and 1 upon L2 with x2. 1 upon L2. Rest are zeros. Are you following?
Yes, sir.
Yes, sir.
Any questions so far?
No, sir.
Okay. The next final job.
Sir.
Yeah.
सर एक्सक्यूज सर टाइम सर होगा सर आई नो सर मैं तो सर क्लास सर ज्वाइन करना पड़ता है
You're having any question?
वो सर
Please write the answer. We have to match. Hello, sir.
Yeah, I'm listening. Yes.
सर वो रिक्वेस्ट कर रहा है कंप्लीट करने के लिए ताकि वो मैच
How much
करे.
are you having to write these two equations? Just quickly write this equation. x1 dot and x2 dot. See, this current that's coming from this branch is sum of these two currents. Okay, first tell me when is your next class? At 11.
11 बजे सर.
Okay. We'll just wrap this process. This current, that's x4. That's the sum of the current going down and current going this way. The current going down is what? C dV by dt. And what's the value? x1 dot. This is C dV by dt. This is sum. This current x4 is the sum of this current and the current x3. So you can get the equation for x1 dot. 1 by C1 x4 minus 1 by C1 x3. 1 by, what's the equation? 1 by C1 x4. Okay, just fill the entries. Minus 1 by C1 and 1 by C1. Rest is 0. This will be 3, wait, this will be 2 zeros. Any relation with x5? No relation with x5. There's a 0 here. 1, 2, 3, 4, 5 entries. The last equation is x2. Okay, let me just write it here. Similarly, this current, that's the input current that's being injected in the circuit. That's the sum of this current x5 and the current that's going like this. I'm just saying this input current is sum of these two current. So if I write this is I equals to x5 is this current, and the current going in this direction. This current going in this direction is also a sum of these two currents, isn't it? Whatever the value of this, the sum of these two. And what's the value of this current? That's x2 dot into C2 C dV by dt plus this current. This current is x4. So you can get the equation for x2 dot. X2 dot is what? 1 by C2 into I minus 1 by C2 into x5 minus 1 by C2 into x4. So for x4 I'm having minus 1 by C2. For x5 I'm having minus 1 by C2 also. And for there's no relation with x1, x2 and x3. So we're having 3 zeros. This is basically 0, 0. This is minus 1 by C1. This is C1 and this is, here is a 0. Let's write it properly. Here is a 0. And we're having a relation with input. That's 1 by C2. No, this is 0. Here, 1 by C2. Is the matrix over?
Excuse me, sir.
Yeah.
Sir, can't we take it I is equals to x5 simply because वहाँ पे L3 and C2 both are having a V2 voltage. So current will should not flow there.
Where?
The
Downwards.
voltage. No. Downwards we'll be having x5.
Okay.
But when we see voltage of L3, that is V2.
L3.
At first point.
Yes, L3 is labeled L3 as V2. Yes.
Yes, V2. And second, then the second instant adjacent voltage is also V2.
Yeah. Yes.
So current should be 0.
Which current? The current going
Which
straight.
is, yes.
Basically, if you see, there is a switch involved in the circuit, but I have not mentioned it here. In the book, there is a switch involved. Wait. There is a switch involved.
Sir,
Yeah.
sir, actually at both the junction there is a wire which has no resistance. Then current can flow through it.
We are just.
This is common point.
This is basically the same voltage. It's a common point. Here is a common point. So current will flow in these branches now. This is a common point. The current is going like this and it's dividing into these parallel paths. And some of the current is
Okay.
It's just like this.
Yes.
Just like this. So whatever current is coming, some of them is flowing straight and some is going down. It's like this. Okay, what's the equation for output? The final equation. I have 5 state variables. And what's the assumed output? Assumed output is across.
So V1. 31.
V1. That's x1. That's x1. That's 1, 0, 0, 0, and 0. Y is x1. So, any question for this circuit?
No, sir.
So, this was your state matrix involving 5 state variables, and this is your output.
सर ये आप 1 कहाँ से लाते हैं ये समझ में नहीं है पिछले भी क्वेश्चन में यही डाउट आ रहा है
This is just don't look at this. Just look at this equation. Don't look at the matrix form. Just look at this equation. Your output is x1.
हाँ
Isn't
सर
it? Your output is x1. How will you write it in matrix form?
अच्छा उसको क्रिएट
Matrix form, this is
करने
like this. If you do multiplication entry by entry, you will get y equal to x1.
यस सर
1 into x1 plus 0 into x2. You will just get y equal to x1, which is your output equation. Your output equation is cx plus du. And this is a linear combination of x and linear combination of u. So your output is just the first state variable. That's why y is x1, and you will get a 1 here.
सर अगर आउटपुट x2 रहता तो सर 0 1 लिख
Exactly. Output अगर x2 होता, then this. Had it been some scalar times x1, then you will
Yes.
scale. The
ठीक है
necessary orders will get 1. Any scalar value. It's a linear combination of these 5. Okay?
yes sir got it.
So I guess time is over. We will just wrap it. We have been recording this lecture also. So if you have any doubts, we will provide you the video. You will just go step by step again and just try to make things clear for yourself. And like you said, we will take some examples next time for multiple inputs also, where we see how we will treat multiple outputs and multiple inputs. So thank you
Sir,
everyone.
can you upload the lectures? Sir,
Yeah,
can
we
you
will
upload
we
the
will do
lectures
one-
on
yes, we will do
Classroom?
the last lecture that sir gave and this lecture. We will be just putting these videos on a YouTube channel. And what I will do is I will just share the link of that YouTube playlist with the CR.
Yes.
And he will
Thank you,
share
sir.
it for
Thank
you.
you.
Okay. Okay. So
Yes,
thank you
sir. Thank you,
everyone.
sir.
You can just leave now.
thank you sir.
Okay. Sir. So recording.